I will talk about, since this is the last talk of the school, I thought we can do something more frivolous and continue with the pixels and show some pretty pictures. But I do want to try also to talk about some more fundamental things as well. It seems at least a lot of the students believe that life is good in deep land, right? You don't need to design algorithms anymore. There is the one algorithm, right? So here is the plan, right? First, you get some training data. Second, you define the objective function. Third, you train the network. Fourth, you sell your startup and you become a billionaire. Okay? Well, actually, there's still the difficulties haven't really disappeared in this deep land. They have just been transferred to these two. So getting training data turns out to be even more important than it used to be. But also, there is the issue of defining the objective function. Okay? So, the training data with our labels are expensive. As I talked about before, we can't really afford to click on them ourselves. So can we somehow use self-supervised training, that is to train on the data itself? So instead of training, having a data and some label that you got from a Turker clicking, can we actually take the data and supervise it with some other data? Okay? So that way we can go through much more data without actually having to actually label it by hand. Okay? Second is defining the objective function, right? So these objective or loss functions tell the CNN what it needs to do. And here, we're well advised to remember the story of King Midas. King Midas didn't think enough about his objective function, right? If you remember the story, he said, oh, can you make it so that everything I touch turns into gold? Not a very good objective function, as it turns out, because he died of starvation because anything he would try to eat would turn into gold, right? Killed his wife too. So this King Midas issue is actually a very, very fundamental issue, and it might not be that big of a deal for you if you think in terms of some sort of a low-dimensional labels, like one label per image kind of things that you basically say, is it correct label or not? So you can do just a classification loss, and everything should more or less be good. But as we go into the more self-supervised tasks where your label is actually a high-dimensional structure, it's a structured loss, then the Midas problem is going to hit us really, really hard. Okay? And so in this tutorial, I'm going to talk about some of the stuff that we have been doing in these two arenas, and they are kind of very much connected. So one is trying to see how self-supervised learning can be used to try to get good features, and also what are the strategies for coming up with the right objective functions while you're doing that. Okay? So the first paper to start us off is now a year old, so it's ancient in today's terms, by my dear former student Carl Dorch, who is now in DeepMind, and it deals with the fact that when people talk about ImageNet, the big story is not that, okay, you can put in images from ImageNet and then it can tell you what object class it is out of the 1,000 classes. That's all nice, but actually that's not really what everybody is using this for. What people use this for is they basically take the learn network, chop off the last couple of layers, and then use the feature representation, the embedding space created by this feature, to do whatever you used to do with hogs or whatever other feature we used to have before. So it's kind of basically you get a learned features and then you plug it into all the other approaches that had nothing to do really with ImageNet. right? And the fact that this works is in a way the big story of deep learning and computer vision, right? Not really this, but the fact that this feature is transferable to other problems. And why would this be? Well, we talked about before that it seems like this feature somehow encodes some of the mid and low and mid-level properties of the image that are more general and generalized to other problems, other domains. It seems, okay. So this is actually the exciting thing, but the question I always ask is: do we need those words? Do we need those labels? Do we need this particular task? Can't we get good features from some other task? Maybe some task that does not require hand labeling. Okay. And so this is basically what we're thinking about, and we know that in text the answer is absolutely yes. So in text there is a whole line of work, the kind of generally called word-to-vec representations, where you want to have a feature for a word, right? So you're given a word, you want to build a kind of a good feature of that word, and one of the kind of classic approaches to that is to do a self-supervised way of using context to define your word representation. The story is basically you take a big book, take a random snippet of text, pick one word in that snippet, and then train the model to predict the probability of other words in that snippet. Okay? So you're basically given a word, you want to predict its context. Okay? And you do it over and over and over and over, and of course you don't need any label data for this because the text is your data set, and you basically create the labels as you go. Okay? And the nice thing is then the representation that this thing learns can actually serve as a very good distance function on words. Okay? And so we were thinking, can we use the same idea for images? Okay? And so here is our kind of self-supervised context learner. Here is the task we want the computer to do. Okay? We've given an image, we take two patches, A and B, and we ask the computer where should B go with respect to A. Okay? And it only has A choices. Okay? So now you are going to be computers now and try to figure out this problem. Where should this patch go? Bottom right. Very good. Now, in psychology, they tell you never to do introspection, but please try to do some introspection. Why did you think that it was bottom right? The what? The wheel, okay. And wheel should be bottom of what? The bus, exactly, right? So you were basically thinking, oh, this thing kind of looks like the top of the bus, that thing looks like the side and the wheel of the bus, and then it becomes a pretty simple problem, right? So you basically imagine that you did not know what a bus was. I argue that this would be an impossible problem to solve for you. Okay? You actually need to know what a bus is to solve this very simple and frankly quite useless task. Okay? So our idea is to basically force the computer to get good or at least decent at this task in hopes that it would have to learn what a bus is. It would have to learn semantics to do this task. Otherwise, it would, this would be an impossible problem. So this is we call it a pretext task. It's a task that we don't really care about, but it will trick the computer into doing something, learning something that we wanted to learn. Okay? And please do ask questions as we go. Okay? So this is the story. We take, for every image, we take a random patch. This particular random patch I picked very nicely. We take 8 patches around it, and then for a random pair, we basically train this kind of a Siamese representation with 2 networks here, and then more shared layers later on, and then basically force it to predict one of the 8 classes. Okay, and this is all end-to-end trained, and it's nothing very sophisticated, except that it took us 5 weeks of training on the fastest GPU. So this is actually a much harder task than something like ImageNet training.
Are the patches always taken at the same distance from each other? Or?
Yes, the scales, it's multi-scale, but the patches are all at the same distance, but you can see that they're a little bit jittered, and I'll get to why this is important. But first, let me kind of sell you my favorite result on this, is that then at test time, we get a new patch. We only use one of the sides of the CNN, right? We get rid of the other one. And then we look at the representation, the feature that you get at the top, okay? And the hope is that that feature, that embedding is somehow useful, okay? So what do I always do when I want to see if a feature is useful? I do nearest neighbors, right? So here is our input, and here are the nearest neighbors from a big data set, okay? Notice, okay, what's cool about this picture?
Nearest neighbors searched on the representation at the top, or
at the representation right here, yes, yeah.
Just out of curiosity, what's the size of the picture?
It's the standard to 2048, I think it was, yeah. Yeah, about 2000. Okay? So what is cool about this? Huh?
Never saw a cat.
It saw instances of cats, but it was only trained on a single image at a time. It was never trained across instances, right? So it was trained on instances, but it's somehow able to discover correspondences within kind of, basically discovering categories. Okay? Yes?
Can you show us the control of the nearest neighbors of the pixel representation of the input?
I will show you control of, I think, hog. Is that, oh, actually, I in 2 slides. Okay, yes?
What was the initialization of the network?
Random. From yeah, we are doing this for Scratch. Of course, yeah, if you start with ImageNet, that kind of defeats the purpose. Yeah, it's we start from random. Okay? Yeah?
that's fire here, just as a binary, and then you is not random.
It's a 8-way. It has 8. It's a histogram of 8 things, and it's trying to guess the distribution.
Some kind of a softmax on the 8
Yeah,
vector?
yeah. Let me. Do I have a? Hold on. There we go. I was trying to hide this, but this is the actual architecture. All right. So you have 2 stacks. Weights are shared, and then you have a couple of fully collected layers and a softmax at the end.
And how big are the patches?
It's multi-scale, but the patch representation I think is 96 by 96. I think. Yeah, they're reasonably big. But I mean, it's drawn to scale. Okay. So it didn't, it took us some time to get this right, because see, this machine learning is the problem with machine learning is that the computer is super lazy. It never wants to do more work than it absolutely has to. So there's always some shortcuts it's always going to try to find, right? So one thing, why do we jitter? Well, we jitter because if you don't jitter, then this is like a easy, like just like your classic Gestalt lines continue thing, right? This is a very easy cheat for a computer to learn to help out with this problem, right? So that's why we have the jittering, and that's also why we have the gap between them, so that you don't get information just across the boundary. Okay, so these things we kind of figured out pretty fast. There is one more not so trivial shortcut that it took us like a month to figure out, and this is actually something that the Shri might actually wake up for, because this is actually kind of a cute little story. So we took these 2 patches, for example, and it did very well figuring out solving this problem, even though there is really nothing in there. It's basically 2 patches of texture, and the nearest neighbors, I don't know what, didn't really look very good, but it did very well for these kind of patches, and I was very, very surprised. And then we visualize this, and this is kind of the nice importance of actually visualizing your algorithms. We visualize that actually what was in common between all these nearest neighbors wasn't their appearance. It was, or maybe some of it was their appearance, but it was also that they were all drawn from the same part of the image. They were all in the lower right-hand side of the image. Okay? And so we were thinking, what's going on? Okay, what is it doing? In fact, we then did train another CNN, which said, okay, let's do this thing. Let's take a whole bunch of patches, put them all in a bag, and then to train a CNN to just predict for a single patch its XY position. Right? This should not work. And yet, it kind of does. So, any ideas? Okay, prospective distortion, no, doesn't work. We tried that. Closer. Yeah? Ah, of course, she would know. Exactly. Turns out, remember, chromatic aberration is that the different wavelengths of light bend slightly different, half a pixel or whatever. And so, I had to make a synthetic figure because on a real figure, you really wouldn't be able to see it. But apparently, for the stupid ConvNet, that's enough to, to go on track. So this actually was the signal that the ConvNet learned how to use in lieu of figuring out what a bus is. Because apparently, this is an easier thing to do than to figure out what a bus is.
How did you figure this out?
There might be other things as well, but so the proof is that we got rid of color and everything worked much better. We also kind of got rid of the red, the green-red axis of color. So we squashed the green-red axis, and things also work better. So there might be other things happening there as well, but it seems that the chromatic aberration at least plays a big role. Okay. So anyway, so this is just a little side note to show that you have to be very, very careful, because this thing is just you don't want to be Midas. Very, very careful. So what has it learned? So here's some nearest neighbor things. So this is the input. This is ours. This is control, which is a random initialization. So this is basically just a random network without anything learned. And this is the best possible thing we can do is trained on AlexNet. Okay, and so you can see that we are not as good as AlexNet, but sometimes we get there, and we are better than random. Yes, Michal.
So AlexNet would learn that different cats at different scales are all the same category, okay? Because it would train on lots of cats. But I assume that your thing would only, when you look for a nearest neighbor for a cat, it would only find cats in the same scale.
We're training multi-scale, so.
No, but when it sees a cat and something near it, if you're taking an image, you're saying training multi-scale, you're taking an image in multiple different sizes.
Yeah.
But your patches are the same size.
But the images are very different sizes.
I know, but it will never see a cat's face in a patch of the same size for a significantly smaller or a significantly larger image of a cat. It would only see this cat with this relative thing only in an image of more or less the same scale. So if you don't train it. No,
I'm not sure I understand. When we train it, it sees cats of all different sizes. As long as small cat can help you figure out the task for a large cat, those representations should get closer.
They would in your case. I understand.
I don't know what that thing is doing. I have no clue.
Did you think that your nearest neighbors actually came from images of different scale of cats? Did you check that?
We didn't look at it. And the multi-scale is not, it's not like a huge multi-scale. It's not like, it's maybe a 2.5 octaves or something like this. It's not like humongous multi-scale.
No, I understand that, but I claim that by the way, it's beautiful.
In general, we know that these ConvNets are annoyingly robust to scale. But we didn't look at this, But
because they say that this cat is in the class of cat, and this cat is in the class of cat, and this cat is in the class of cat, that's why we'll learn that cats of different scales are all cats, okay? But what you're doing, since you're using a patch of the same size, when it saw at some images faces of a cat and it understood the relative position and therefore from that it learned, it would only be for this particular scale.
I don't think so, because if it can use this other scale to help it do its task, it should bring them close. Okay, we can get this online.
Alyosha?
Yes.
Why do you say that yours is not as good as
Okay, so I think these are the good results. Sorry, these are the results where we are not as good, and this is my favorite one, which is basically sometimes random is just as good. And in fact, we have seen some other papers from Gaddis that show that, for example, for texture synthesis, random network is just good enough. So it's random. Just you initialize with Gaussian noise. You initialize your network with the Gaussian noise, and then you just do nearest neighbor in that representation.
But it's still learning. How is it?
It's not learning anything.
How is it doing it? How is it accomplishing anything?
It's like hog. Think of it as like a fancy hog.
This means that you run a lot of filters.
Yeah, it's like multiple random projections kind of thing. Yeah, random projections. It's the kind of the structure, the architecture of the network is enough. So you can think of hog as a kind of a simple 2 or 3 layer convnet, right? And hog doesn't need to learn any weights. It basically just does its thing, right? So yeah, I think it's kind of, if you think of a random projection analogy, and it's kind of cool that for something like wheels. And this is, by the way, also wheels were the killer example for hog. Hog really liked wheels. So in a way, it's kind of nice that there is kind of some similarity here.
Bill's question. Did you compare it to regular nearest neighbor on the image on the catch itself?
I didn't. We didn't because we know that, for example, for the wheels, we tried it for hog and image and SSD on pixels, and hog does work better. So we're kind of building on that. Yeah. Yes. Not as good. The data, the training data set is exactly ImageNet. It is exactly ImageNet without the labels. Okay, so it's apples to apples. I haven't said anything about. I'm not making any claims yet. I think the claims come next. Yes, there you go, claims. So then we actually wanted to see if it's actually going to do anything, and so kind of the standard framework is RCNN, right? RCNN is basically trying to solve detection in Pascal, and there is not enough data in Pascal itself. So what standard thing that everybody does is you initialize your network with weights from ImageNet, and then you fine tune on Pascal. That's the kind of the standard thing that everybody does. And of course, what I wanted to do is to see if we can just insert our own pre-trained features here instead, and do as good as Pascal, do as good as RCNN. Okay. In fact, I was so sure that we made a bet with Jitendra Malik, and here are the witnesses. And the bet was, this was in 2014, if by the last Thursday of autumn of 2015 a method will exist that will match or beat performance of RCNN and Pascal VAC without the use of extra human annotations, Mr. Malik promises to buy Mr. Efros 1 gelato, 2 scoops. Well, let's see where we are. So this is ImageNet labels. This is what we want to beat to get the gelato. This is what you get if you basically have no pre-training, right? This is just you start with from scratch, from random, and then you only train on Pascal. And this is what you get with our thing. So we're about halfway. Well, we tried to push it a little bit. One way to push it is to use the old classic story that if you initialize, instead of random initialization, if you initialize with something like k-means, things are better, and everybody is better, and we are better, that our improvement is higher, so we're pushing a little bit further. The other classic thing that people do is just get a bigger network, and so we run it on EDGG, and we're getting there. I think the difference is squishing, but still no gelato. So this is Jitendra getting his, look at the smug face. So let me give you some advice. Don't ever bet against your advisor. You will not win. But still we're still hoping. And interestingly enough, for things that are somewhat less semantic, for example, normal surface reconstruction, using, for that task where people have used ImageNet, using our features actually matches, or in one case beats, the ImageNet. So it seems like the less semantic the task, the more this helps. Okay. So far we made made sure that our self-supervised label space was very low dimensional, right? It was basically an 8-way classifier, right? Exactly because that makes the loss function very, very easy. It's just classification. Okay. That's not always possible. So the next thing we tried is to try a more kind of frontal assault onto this self-supervision thing and see if we could train a network for the task of colorizing images. Okay? So it's an interesting task. It's more interesting perhaps than the context task, because some people might actually be interested in that. So you have a grayscale image, and we can tell at least some of the colors. We know that the sky is going to be blue. We know that this is going to be green, right? This is going to be reflective, and so it's not that crazy that an algorithm could be able to hallucinate a colorization of this image, right? And so that's exactly what we set up to do. So we have an input image, and we basically given we go for in the LAB representation. L is the intensity, and then AB are the chromaticity channels. So we're basically just train a very kind of straightforward network to predict this from this. Okay? So we're basically, now you think about it as, instead of predicting one label per image, we're predicting one thing for every single pixel, right? Kind of regress to the two channels. Okay? And then you put them together and you have a colorized image. Okay. And of course what we're really interested in is that, look at this. This is again free training data, right? Because just take any image you want, split it into two parts, and then you can train one from the other. Okay. So then we also wanted to see how good are the features that learned from this way. Okay. So the main, these slides used to be very funny, like a half a year ago. Yeah. So the fundamental issue that why it's finding the right loss function is tricky, is that there is an inherent ambiguity, multimodality in the problem statement. So for example, here is input image, and here is our colorization, and it looks pretty reasonable, except that the ground truth colorization is quite different, right? So these are kind of another mode in the distribution. Now we think that our mode is just as good, maybe even better, but if you think about it in terms of just regressing to the ground truth labels, the kind of a L2 regression is not going to do well in this problem, right? Because it will basically try to find the mean of all those modes, and the mean is probably going to be just gray and boring. Okay? So that is a fundamental problem with a lot of these things where you have a multimodal distribution. So instead of the regression, we turn this problem into a multimodal classification. So we divided our 2D color space into, I think, 330 something parts, and then basically made this into a classification problem to come up with a distribution over these labels. Okay, and so the nice thing here is that then you can capture multiple modes in that representation. So for example, here is a little birdie, and you can see that sometimes it thinks it's a blue, but sometimes it thinks it's red, and both blue and red modes are present here. Or you can look at the background, and sometimes it thinks the background is green, and sometimes it thinks it's yellow. Okay, that wasn't quite enough, because still, whenever you set this kind of problems up, the network does, any learning algorithm just wants to keep it safe, right? And so we ended up with images that were very desaturated because you don't want to make any sudden movements, right? And so and also if you look around in our world, there's a huge class imbalance. If you look at this room, for example, 60 or 70% of pixels are white, right? So you need to kind of find all these colorful things. And so we have to basically normalize and do class rebalancing to push those rare colors out there so that the network is willing to use them. Okay? So here is the network. So we take the standard network and then we take away the fully connected layers. Remember what Rob was talking about? We get rid of them and instead we kind of make what's called a decoder by pushing the network, making it fatter again with what's called a atruv or a dilated deconvolution. Okay, and you can read up on the papers what it actually does. And then finally, basically, you go and you end up fanning out to the full image, and then you predict for every pixel, you predict one of the 313 color labels from your distribution. And then finally, and this is not actually part of the network, you have to actually take the argmax and actually produce an output image. Okay? And so let's see what it does. So this is the input image. This is what happens if you just do L2 regression. And it's actually pretty good. And the reason it's pretty good is because the sky is always blue and the grass or the trees are always green. So there's only a single mode really. And so there is really no contest here. There is nothing we gain here. But if we take something like this, L2 gets you a very kind of desaturated, boring look, right? Because it's basically trying to average a whole bunch of things together. Whereas our thing is quite more colorful. And again, notice that if you look at the actual ground truth, our ground truth is quite different. But we argue that ours is maybe just as colorful and perhaps just as good as long as you are not a big bird expert. Can you repeat again this rebalancing thing? You're basically just reweighing the rarer colors more in your classification. So the rarer colors get more weight than the frequent colors, just because the rare colors are the more saturated ones in there. Yeah. Yeah.
Doesn't the rebalancing hurt your validation performance?
Yeah. Good, very good point. The problem is, how do you validate? So actually, this is a beautiful seg, I believe. Okay, some failure cases, and Yair's like, oh, you should have used MRF. We tried MRF, it didn't help. Sometimes it kind of forgets what it's doing. So there is kind of spatial things, but we have some ways of tackling this later. Sometimes the biases in the data set are kind of cute. So it had seen a lot of dogs with tongue stuck out, and so it's just kind of putting that tongue in the dog anyway. So how do you evaluate this? Well, you can do per pixel accuracy, PSNR, whatever, but that's not really what you want to do, right? Those numbers are not really very meaningful for perception. And so instead, what we did is we actually tried to compute, some perceptual studies, and also we can look at the representation learning. How well do these features work for all the other tasks that we talked about? Yes.
Classification. When you move from regression to classification, then if the labeling is close, but not exactly the same thing, you lose that.
Yep.
That closeness in the
I'm totally with this. Yeah, this classification thing is killing signal. It's a bad thing. I would really love some great machine learners to come up with a way to do regression and be multimodal. But I don't know how to do it. Yeah, so
I feel like we should be talking about GANs.
we're coming. But but this is classic statistics.
Totally get rid of the loss function and put a GAN there.
Okay, hold on. It's coming. Yeah.
How do you coordinate the different parts of the image will fix the same mode?
And that's exactly why you have this. That is exactly why the kind of the long range connections. There is some long range connections because of the structure of the network, but sometimes that breaks down, and that is a problem. And by the way, that's a problem with GANs as well. So the GANs seem to have.
Take this image and generate a pyramid, a Gaussian pyramid of it. The colors have to be consistent, but then long ranges would become short and low scale.
Well, there is kind of a pyramid inside of the network already.
I know, but
But-
you're doing a pixel labeling of color.
Right.
And here each pixel would have still to be, it still is a natural image. It still would have to have a consistent color, but it would have to also be consistent with the colors of all its neighboring.
I think we tried a Laplacian pyramid in there as well, and that's one of the problems with these deep networks. You just, huh?
I was actually talking about the Gaussian pyramid.
Oh, Gaussian pyramid. I see.
Because of the
I see.
redundancy.
I see. We haven't tried the Gaussian pyramid, but it's very hard for this thing to figure out. To nudge this thing to do what you want, right? It's again, it's the Midas problem, right? It has a mind of its own.
Have you, I see you didn't use skip layers or hypercolumns?
Not us. We have a competitors that did use skip layers, and I will compare with them. We actually do better, but skip layers are in general good. Okay, so let's just really quickly look at what we did, and we basically just ran a mechanical Turk study. We show one image, show another image, and then we ask people, is this fake or is this fake, right? And the second one was obviously fake, so everybody got nobody got fooled in this case. Let's try something a little bit more hard. 1, 2. Okay, clap if you think this is fake. All right. All right. Well, you guys got fooled actually, but there's a group think bias here, but it's about 50-50 for this image, and this one. All right. So this one, a lot of people got fooled, but it's also kind of not a very fair thing. The cool thing is that the network has a mind of its own. So, for example, we found this kind of image of somebody tie-dyeing, his dog, and then we gave this image to the network, and then it actually thought, no, this is much better colorization. Or something like this with this kind of crazy Yoda, and it's like no. So what's where we are. The ground truth is 50-50. Random is about 13%, and we are doing respectable, not great, but respectable. And this is our competition, which use skip layers. But they were really all focusing on PSNR, and so that might be why. But you can say, well, how does it work on actually legacy photos, right? Not something where you actually separate yourself, the color from the grayscale. What about actual true grayscale images? So here is some examples. This is an animal that went extinct, so nobody actually knows what it looks like in color, and and here is Richard de Zhang, the first author's grandfather from Imperial China. This is some French people having a picnic, and we can even do some migrant mother is also doing kind of okay. Okay, and there's tons of things online that you can try this out on your own, photos and videos and stuff like this. But of course, more interesting for me is how good are the features? Yeah.
So still, these historical, they look less good, the results, than I would have expected. What's the, what do you think is being so different here from the training set that kind of makes it difficult for the network?
I think part of it might be some of these kind of low-level things, like remember the chromatic aberration turned out to be very useful unexpectedly. There might be something in modern cameras or in higher resolution images that it can latch onto, but I'm I mean, and there's also kind of the classic data set bias. They're drawn from different distributions. Turns out we also were worried that they might be learning something very, very low level. And so that's why we kind of looked at this little experiment. We said, okay, let's take an image with two, equal luminant, more or less, vegetables, and then see if we can colorize it. And, it actually does, there's some artifacts, but it actually colorizes them in the naturally semantically correct way. Whereas if you take Macbeth-Thorel chart, which was not in the training set, it doesn't know what to do with it. So it does suggest to me that it is actually looking at some semantics, that it's not just some low-level signal that it's picking up on. Okay? And that's why we thought, okay, let's see if we can use this as a self-supervised training signal to get our features. Okay? So again, this is our kind of supervised training. And we can think of a self-supervised training as basically taking our data vector x and then splitting it into two parts and using one part as the training signal as the other as the corresponding training data. So you put half of your image, for example, as the x and the other half as the label y, right? Or in our case, take one color channel as the input and the two other color channels as the label. Okay? And and so we can see how good the features are. The first thing to do is to look at somewhere inside of the network and see what it looks like, so we can visualize neurons. So here is just kind of a visualization of a particular neuron that we found to be looking good. These are totally picked by hand. So some of them seem to code for stuff, and some of them seem to code for things. So again, it trained a neuron that is looking for faces, which is kind of cool, or dog faces or flowers. Okay, so that's encouraging, but let's see how it actually does on some data, on standard tasks. And again, we have this is our top 100% is the ImageNet label performance. This is 0% is basically your Gaussian untrained network, and so autoencoder is the classic thing that people do to train features. You basically try to replicate your input image directly. Doesn't do so well. This k-means initialization does actually surprisingly better. And here are all the kind of all the other methods. And red is the Dorch et al. Is the one that the context thing I talked about before. And this is our colorization thing. So it's kind of surprising that it does as well as it does, right? We were very surprised because in the previous one we really wanted to kind of try to figure something semantic out. Here, just colorization. So it might be that color might act as a kind of a proxy for segmentation, right? It might have enough signal in there to learn about segments in the image that's where it kind of could be useful. But again, we don't really know. Okay. And a final little nugget. This is submitted to CUPR. Is we think about autoencoders. Autoencoders is basically you have an input image, and then you want to reconstruct that input image, and the features learned here are there's a bottleneck so that you don't just copy it over, but those features, the compressed features, are supposed to be a good representation. Turns out they're not really a good representation, and people have tried various things. And what you can think of what we talked about before in the colorization is kind of like we call it a cross-channel encoder, right? So you give half of the data, and then you're basically trying to encode the other half of the data. So it has to work harder. That's why the features are better. But it's not quite an autoencoder because you can't really use this on new images because it's only seen half the data, right? It's leaving half of the signal on the table unused. So what we decided to do is the stupidest, dumbest thing. We tried all the clever things first and it didn't improve. Just put next two cross-channel encoders next to each other and basically solve both tasks at the same time, and then treat the representation, the joint representation, as your feature. Okay? Very, very simple. And we can do it for color. We also did it for depth. And the images here don't actually look that great, especially going from AB to L. It doesn't really look that great. And we also had it with RGB to D and D to RGB. But interestingly enough, in terms of performance, it was working surprisingly well. It was basically, at least as of like 2 weeks ago, I haven't checked archive over the holidays, but as of 2 weeks ago, this is the best performing thing on this task. Which kind of sad that it was so simple, but maybe there is something to it. Okay. So we talked about, okay, you go from regression to classification, and you tweak your loss function and things become better. Another way to tweak your loss function that seems to work pretty well is to limit the space of outputs that the network is allowed to produce. And here I'll just very briefly mention this very simple work on view synthesis. I think somebody already talked about the problem of view synthesis. You're given an input image, and then an angle, and you want to synthesize new views of that object. Okay, and kind of there is a classic way, baseline due to Brock's, very classic. It's like half a year ago, right? Very old. That basically just makes it into yet again one of these encoder-decoder networks. You take your input image, input view, you encode it, you also give it a viewpoint transformation, and then you put it all into one feature vector, and then you decode it back to a new view. Okay? And it seems to actually work pretty well. The only problem that it's again suffering from that same multimodal problem, right? That it's basically making things blurry because it has multiple things it thinks of doing, and basically L2 or L1 just averages them all to be the mean, and the mean is going to be blurry. Okay, and so here we solve this problem in a very even simpler way, which is that we, instead of synthesizing pixels, we kind of made it into kind of a texture synthesis problem. Instead of creating pixels, we decided to steal them from somewhere else. So the only difference from the Brock's paper is that instead of spitting out pixels, we're spitting out a flow field, a vector field that says where should you go in the input image to steal your pixel from. Okay?
You learn the warp.
You learn the warp, yes. You learn the warp directly. You're training to learn the warp. Yes, exactly. Huh?
3D, right?
No, 2D. It's all 2D. It's all 2D. Yeah, right. And the kind of cool thing is that you think, well, you can always learn the warp to create a picture of me out of Mona Lisa, right? You can just steal the right pixels from the right places, and you need to have some other constraint like smoothness or something to have it move smooth chunks from here to there. But we didn't actually have to even add any smoothness constraint, because the smoothness constraint is built into the convolutional nature of the network. So it already wants to be smooth. It already doesn't want to jump around. And so all we did is we just made it produce vectors instead of actual pixels. And let's see, do I have okay, and there's a picture. So green is the input image, and all the other views have been synthesized. Okay, so you can see that it's quite a bit more detailed than the simple pixel generated L2 thing. Okay, here's another example. This is for a real car. Okay? And you can also see that basically, the pattern of as you go away from the source view, it gets worse and worse, but at least when it's close to the source view, it can steal more of the pixels and it actually gets better. So it kind of gives you this graceful degradation. The farther you go from the source view, the worse it gets, but in a kind of a nice, smooth way. Yeah?
What are the labels for this optical flow? How do you, what is your ground truth?
Very good. So ground truth for this are 3D models from ShapeNet. So we render 3D cars from multiple views, and we get the angle also. Yeah. And then we basically, but it's still pixel images to images. Input image, and then another input image, the label image, resulting desired output image plus an angle. Yeah. No, there was, okay. Yeah, oh, sorry. Go ahead.
You never get any flow for the background?
There is, I skipped the thing that we're also estimating the mask so that we don't do the background. Yeah. Yeah. And we also have results for doing it for scenes, not just objects, but it doesn't work as well.
So can't you do this on classical optical flow data sets? You have data sets that they give you the disparity. There's a lot of work on optical
Right. So we did this for Kitty, for example. You need the optical flow plus you need the camera
calibration.
So because you need to know the transformation. So Kitty is such a data set, for example, and so we do have some results on Kitty, but they're not as good because it's a richer space. Here you basically this is very much what we were talking about before. This network just works on cars, right? You give it a vacuum cleaner, you need to retrain your different network, right? So it's a smaller space. Okay?
Did you train on different cars or just sedans, or does it have like trucks and?
I think it's passenger cars, but SUVs are in there, yeah. But not trucks and no buses.
Is the motivation here still pre-training for semantics?
Here, no. Here, I'm kind of pushed back the pre-training story and kind of more into the, what are the various things that we can do to get better losses. So this might very well, we haven't tried. It might very well be that doing this, predicting flows might actually give us better features. We haven't tried.
Do you have an intuition on why it can't generalize to all the cars? Because the 3D flow is the 3D flow. It doesn't matter.
Yeah, but remember, you're dealing with. I mean, if you have a side view of a car, how would you know how the front of that car looks like? You actually need the data. You need to actually know what a car is, right? So a side view of a vacuum cleaner might not, knowing a lot about cars might not tell you anything about how the front of a vacuum cleaner looks like from the side. So I'm not sure that it necessarily is to be expected that it would work across categories. Yes. Yep. Okay, so finally, let's try to tie this all together. So, so far, for every application, there was one little nugget of, okay, this is one thing we can do, this is one thing we can do. And how did we do it? Anyone has a guess? What's the algorithm for finding the right loss function? Well, the algorithm is hack until the results look good, right? It's also known as the gradient student descent. I highly recommend it to the senior members of the audience. It's very effective, but somehow unsatisfactory, right? Especially for the grad student. So, can we actually, operationalize this notion of looking good? Can we actually have some way to say this is a good image? And this is where we end up with the last topic, which is this wonderful paper that kind of burst into the scene. Well, it kind of creeped into the scene in 2014, and then people slowly figured out its power. It's the Generative Adversarial Networks by Ian Goodfellow et al. And I'm going to try to give a very brief summary for those of you who don't know what it is. The idea is the following. The idea is that you have you want to have a generator. You want to generate some pixels, images, right? Just like what we have done. Let's say in the most general case, you want to start with some sort of a random number and generate a corresponding image given that random number. Okay, so you're trained on a data set of fish, and then you have some point in that Gaussian, and then you want to generate a particular instance of the fish. And it might do something like this, which is kind of fishy, but not very good, right? So, and we don't even know if it's good enough or not, right? Because we don't even know how to evaluate what's the loss on this. So what they propose to do is also add a discriminator, okay? And the discriminator is going to take in an image that could either be an image generated by our generator, or it could also be just a perfectly good ground truth actual photograph of a fish, okay? And its goal is for every input image to say whether it's a real image or it's a fake, generated image, okay? And so in a way, this is basically the ultimate loss function for computer graphics, right? It's basically trying to do, what's it trying to do? It's basically the generator is trying to fool the discriminator so the discriminator could not be able to tell the difference between real and fake. This is exactly what we were testing our human subjects on in colorization, right? Give two images and you should be at 50 a chance whether it's a real image or an image generated by our algorithm, okay? And the insight here is that you basically optimize both of these guys together. You have the generator and a discriminator, and they feed into each other, and they basically have kind of a minimax optimization until things get good, right? So just a reminder for those who don't remember, the difference between discriminative and generative models, right? So a generative model is trying to create, it's a probability of data plus the label. So you're an artist. You want to create, let's say, a zebra, right? And also create things that are not zebras. Whereas a discriminative model, it doesn't care about creating a perfect description, right? It just needs to create to doodle enough so that your zebra is going to be discriminatable from other things that are not zebras. So maybe you just put a few stripes there and that's enough. That's a zebra. That is enough to separate it from, say, an elephant, right? And so the discriminator actually doesn't have to work as hard, right? And it's also often much better, right? So this guy is solving a simpler problem, but really what we want is to generate beautiful images. So the idea is to use both of those things together. So the adversarial networks simultaneously train two models: a generative model G that captures the data distribution, and a discriminative model D that tells whether a sample comes from a training data or not. And in the end, hopefully, the G recovers the actual data, the distribution of the data, and D is totally confused, so it's uniform. It's a chance everywhere, right? That's what you want to happen. Fortunately, that doesn't actually happen in practice, but that's at least the desired goal. Okay, make sense? Okay, so here are some of the examples from some of this work. You start with random noise and you sample and you can create faces that actually look pretty facey, right? That's kind of that's the best. They're not, for graphics people, this is still not good enough, but for machine learning people, this is actually pretty good results. So in this case, again, you have your generator that generates from noise. You go to faces, and then you put in a discriminator on top that says is it real or fake, and the discriminator also gets to see a whole bunch of real faces, and this is the positive example for the discriminator. It says, okay, no, this is real. Okay, and so you train both of them together, and there are some limitations of this thing. They're very, very hard to train. They get stuck very easily. Discriminator, as we discussed, it's an easier task to be a discriminator, right? So it tends to wean too easily, too fast, so that the generator doesn't actually get to learn that much. Or there is a more subtle problem called orbiting. In evolution, it's called co-adaptation. So you have like two species, and like they are orbiting around each other. So like the generator makes a mistake, and then the discriminator slaps it down, propagates the error, and then the generator makes another mistake, but it forgot about the previous one. So it's kind of it gets you these oscillations. Okay, and also it's not quite clear, why we would want to sample randomly from, at least for graphics folks. Why would you want to randomly sample from random numbers to get images, right? And so this is where it's really the work of my wonderful postdoc Philip Isola, thought, okay, maybe we can A, try to get these GANs to work better, and B, actually make it somewhat more useful for graphics folks. And we call this task image-to-image translation. And the idea is basically to unify pretty much everything I've been talking about today, whether you have an image in and an image out, and you want to do something in between, whether it is to go from grayscale to color, or from one view to another, or whatever. Okay, and so that's basically was our goal, to find a universal loss that we could just plug in any paired data you want, and it should just work. Okay, so the proper name for this is conditional GANs. So here, instead of conditioning on a random, or instead of giving a random number z vector as your input is the input to this image-to-image translation. You can also think about it as image analogies with more than one pair of images, right? So it goes all the way back to, or texture transfer, right? This is all the way back to 15 years ago. But now we can do it with a whole data set. So we are given this is a view, satellite view of from Google Street View, and this is the corresponding Google Maps image, and we want to translate from here to here. And so the idea is to basically, instead of having a generator start with a random number, we have a generator that starts with, let's say, a map view and translates into a satellite view. Okay? And now our discriminator, instead of just saying, is this a real image or not, we actually wanted also to force it to make sure that the translation actually makes sense. So the discriminator gets both the output of the generator plus the conditioned part, and say, does this pair look real or fake? And so in this case it's fake, and in this case it's real, right? So now we are basically, our discriminator is now looking at pairs instead of single images. Okay, that's basically the main change. And we don't have any kind of random initial input. Instead, we are doing dropout at training time and test time to kind of get a little bit of randomness in there, although it doesn't really work as well. Okay? Yes?
Is gradient back from the real or fake pair to generate the pixels of the image?
Yes, that's right. In fact, there you go. Right? So kind of the cool thing here is that as far as the generator is concerned, its loss function is the discriminator, right? So instead of having a hard-coded loss function, the loss function is actually learned. It's the discriminator. It's the discriminator. Okay. So now we are basically making it so that instead of designing the loss function, we just get the discriminator to do it for us, hopefully. So far, so good? Yes?
What are the features learned by this discriminator?
We have not looked at the features. All we know is that, unfortunately, the discriminator is not universal. It would be amazingly cool if you can then now take this discriminator and just apply it everywhere, and all the world will be wonderful. So it seems like the discriminator is really very much tied to the generator. It's really only working for that particular generator, because it's basically, that's the stuff, that the generator is only going to generate some small part of possible things. And so the discriminator is basically tied to that guy. So unfortunately, but I'm sure like gazillions of people are working on this. So mhm.
There's actually a theory that says that in the limit, the discriminator will have no information. It will tell you nothing about what images should look like. The best discriminator. When there is no when it's perfect, there should be no information. But yeah.
When it's not perfect, does it have any semantic specificity?
I don't know. We haven't looked at this. This is okay. The thing is that we posted this like before the holidays, and somehow it's already like I'll show you some. Yeah, it's early days. I'm gonna skip the architecture. The only thing to say that we actually now we are using skip connections to answer the and they are helping us a lot because here you can think about it. In a standard encoder decoder, it's kind of you're squishing things. You're compressing things into some kind of low dimensional representation. But a lot of the things in this kind of image-to-image translation might be some kind of a very simple things. You maybe just change a little bit of color and you're almost there. So we also want to give the thing opportunity to just kind of go directly without the bottleneck. And that helps a lot. So here is some of the kind of effects of the different objective. So here we have this is the street scenes data set. This is semantically segmented, and then it's basically trying to produce the actual image that was used to segment to get the segmentation. And here it's the same thing, but for I think it's Zurich facade data set, where given an image, this is the segmentation it got. And so now we're trying to go from this segmentation to generate the actual facade. So this is the ground truth. This is what happens if you do L1, which is nothing good. Okay. This is what happens if we have this conditional GAN. Okay. And this is what happens if we have conditional GAN, but also add a little bit of L1 to kind of keep it in the right neighborhood, because we found that often just the conditional GAN can still run quite a bit away from the original conditioning that it was given, because there is nothing really that really forces it to be faithful to the conditioning.
So again, what's your input to the network in this case?
The input in this case is this image. Okay, and the output, well, the one we like the most is this one. So we go from here to here. Okay.
And your gun would get both of these as the GAN would generate, not GAN,
So at test time, it's just a generator, right? The discriminator is only for training. Yeah. We throw away the discriminator at test time. The test time is just the generator. It's basically just the loss function that we trained it with, right? So here you can think of this conditional GAN as a loss function that the generator was trained with. Yes?
So at training time, for the GAN, you need to give the input and the ground truths.
Yes.
Could you only say, but you have the ground truths.
Mm-hmm.
Could you only say, is it fake or is it not fake?
Well, but no, I'm not quite sure what you mean.
Okay, offline.
Okay, yes. Okay. Yeah.
Well, it's kind of a tricky point, but
Uh-huh.
automatic uses loss function generation. If you keep on adding terms to your loss function, so you get a result that you like.
That is a very good point, but it's kind of like what is it? If you had when I started grad school, right? If you have one image in your paper, it's a hack. If you have two images, it's an algorithm. If you have three images, it's a framework. So here we have 8 different data sets, and the number of things we tried is 2. So one can argue that, and we have added data set after we have settled on this combination of this. But very, very fair enough. And some people actually like just the CGAN version as well. So that's not such a bad result also. So our own main argument is these two are way better than this, which is what we would hope. Okay. I'm going to skip let's look at some results. So this is more results on the facades data set, going from the input to the outputs, ground truth versus what we get, and it's still not something that SIGGRAPH reviewers would be happy with, but it's definitely, I feel like, getting there. I feel like there is definitely progress.
When the generative system chooses a particular building color, if you look at a lot of them, you say it might be grayish, but then it shows a bright orange one.
Yeah.
Do you know what it's doing? Like, how does it decide?
Again, we can only speculate, but it's probably thinking if I choose gray, then it would not look natural, and so the discriminator will call me on it. So maybe it starts with gray, and then the discriminator says, no, I can see through this. And they say, okay, I'm going to fool you by picking some kind of a building-y color.
Are you seeding it with a random number?
No, we're actually not seeding it with a random number. We have, the only randomness in there is dropout, so that basically we get rid of randomly some net neurons, both at test time and training time.
That's training.
Also in test time. Also at test time.
At test. So
Yeah.
I guess the question is, if you gave it that input in the upper left corner,
Yeah.
how different would its generated outputs be if you reran it multiple times?
It would be very similar. That's another issue that we don't really know how to deal with. The kind of sampling from this doesn't seem to work very well. It likes particular thing very well. I mean, it can be different, but in reality it's not that different.
It'd be interesting to explore with perturbations.
Yeah.
Right? Just take
Yeah.
your upper left input and change, the blue bar to a little bit bigger blue bar and see if does it flip colors.
Oh, this thing, like, I see. I'll show you something. I will show you something at the end. Yes. So this is the street scenes again. We can do both ways. It doesn't need to be one way or the other. So we can actually produce like segmentation results with this same method. They are not state of the art, but again, it's exactly the same code, exactly the same parameters. You just plug it in and run. We can do it for maps to satellite and the other way around. Again, perfectly fine. We run it on our colorization, and the results are, I think, slightly, maybe for it. They're less noticeable artifacts, but it's still not quite as good as we hope it would be. We can do things like day to night from the paper of I think Bill. Were you on this paper? Yeah, Bill and Fredo. We can do it from edges to images. And the coolest thing here, so this is pretty cool, but it's okay. We know that edges have a lot of information, right? Gradient domain stuff that kind of tells us that edges contain a lot of information. But the cool thing is that now we actually train it on the edges and test it on human sketches from James Hayes' sketch data set. And I really like this. I mean, look at this boot, right? It's trying to do something, and it's okay. Maybe see it on the monitor is you can see it better. It's doing something, right? And it's again exactly the same algorithm, exactly the same parameters. And this is where I will tell you this is the new way to do research. So we posted this thing, and Phil was very good. He posted on GitHub all the code. Very easy to run. You don't need to know anything. Like high school students can run. You just give it 2 directories of input and output, press run, and it does things. And then we went on vacation, and then somebody told us check out Twitter, which I don't even know what it is. But apparently now with Trump we will have to learn what it is. But like people have been like running it and just like we do not need to do any work anymore. So there's somebody who colorized classic movies. There's some Japanese art people. I don't know what they say. And this is just random. I just picked it up. Let's see. This was a very cool one. So somebody basically ran it on a tablet and with a sketch interface, and it's working. All the credit goes to Phil because really he spent. We had something working in like the end of summer, but then he spent the whole fall getting rid of things, just getting rid of different parts of the algorithm, trying to make it simpler and simpler and simpler. In the end, it's actually very, very simple. And I think that's kind of the the success of this is that it's really, there's nothing extra there. Let's see if there's any. Yeah, a lot of Japanese for some reason. There was another thing I liked. It always changes too, but there was some guy who was doing it. This one? Yeah, I don't know what he's doing. I think it's the same thing. No, there was some guy who was doing like a style transfer between him and some famous speaker. But I don't know. Oh yeah, and it can do depth. You know, people use it for depth estimation. People have designed cities with it. Yeah. Oh, there you go. Yeah. Kind of weird, right? So this kind of a do as I do thing that I did like 15 years ago, and it's it's not great. But again, this is like one frame at a time, right? So there's nothing. It's just completely out of the box, and these people are probably like high school students. So yeah, you guys are very welcome to use it. It's online, and hopefully there's it will get us closer into understanding, how to generate images with this thing. So to conclude, ComNets have moved the difficulty from algorithm design to the quest for data and the loss function design. And so, we should all remember about Midas and keep this in mind as we design our loss functions. All right. Thank you very much. Do we have time for, well, not really. Why don't we just move the question session to lunch? That sound good?